if I'm remembering properly. It's either right before or right after the midterm. It depends on how everything falls this quarter. When we start getting to where we cover that stuff, then I'll tell you and give you a week notice, just like we did this time.
And so the midterm's November 2nd, right?
I think that's what's on the books now.
It's like right after Halloween.
Well, a day. You should be over your hangover by then. Yes, it is early November. I think it's either. Oh, let's see if we can pull it up. Just have to wander through my. Oh, let's see if we can pull it up. Just have to wander through my. Let's see. So we're going to have 2 weeks of digital labs. So bring a computer if you have one. Next few weeks, labs, Excel stuff, and some simulation stuff. Just because when we do quantum, there's a lot of times there's things we can do on the computer that work out better than what we would do in a lab.
In the computer lab section.
Undetermined. We'll see. And then yes, our exam is beginning of week 7. So we are right here, right? It's today the 14th? Yeah. So we've got 2 more weeks of lectures and a week before the test. So the Tuesday of October 26th, I'll give you last year's midterm so you can start practicing with it. And know exactly what the format of the test looks like. And we will probably not do those other 2 quizzes until after the midterm because it'll be after, we need to cover bonding and nomenclature. So probably the week after the midterm, you'll have your next closed book quiz.
And we're actually going to do a full day of just exam review?
If we have time. Realistically, what winds up happening is I'll wind up having like 5 slides left over that we need to cover. And so it'll be like a half lecture and then followed up with you guys just asking me questions or doing example problems. So it'll be somewhere between a full day of exam review and me getting to through the rest of the material and then exam review. Right? Let's see if I can get out of that now. All right. So, but that's all in the future. That's future Sean's problems. Where's my cursor? Where'd he go? For today, we're going to talk more about orbitals and how we can use the periodic table and what the periodic table tells us about these orbitals and energy levels. So, a couple of good quiz questions though. First, just for fun, are humans incapable of thinking about the future when making decisions? Turns out, yes. We can think in consciously, this is a good decision for my future. But basically, when we make those decisions, our brain weights things. It's a weighted average. You have 2 options. Your brain is hardwired to prefer immediate gratification or immediate benefit over long-term benefit. Because of the way we've evolved, an immediate benefit always happens versus a long-term benefit may or may not ever actually happen. And so even though now we can say with a lot of certainty when something is going to happen 15 years from now, it's still something that our brains don't process very well. So unfortunately, that means that we're not very good at planning for our future as a species or as a society. We're much better at thinking about the next 3 weeks. That's just how our brains work. So you always have to make a conscious decision to think about that and know that your brain is fighting you on that. You refer to your lizard brain, right? The lower, less evolved form of your brain that's more concerned with immediate benefits and basically keeping your belly full from an evolutionary sense is going to take over or have a bigger say than you want it to on a lot of these things. So just keep that in mind when you're deciding whether or not you want to keep sleeping or go to lecture or take that hard class or the easy class. I'm guilty of that. I was a math minor, but I didn't take differential equations because it seemed hard. I took a really fun, cool class called discrete math instead that was not nearly as helpful for me when I got to grad school. And as a result, I wish I had taken differential equations, but I was not capable of weighing the pros and cons adequately when I was making that decision. Why are humans still so tribal, even though we should be more connected than ever? This is another good one, and this is sort of just good life advice. This is not science related, but this is just in the nature. I don't know how much you guys know about sociology and theory of the internet and how cultures form. But basically, what the internet has done, even though it supposedly has made us more connected than ever to each other, it's allowed us to only connect with the people we want to connect with, which for most people is people that we agree with. So it's resulted in this fragmentation of instead of needing to be able to be kind and be on good terms with everybody in your town, whether or not you agree with them, you're able to ignore the people in your town that you don't want to talk to and go online and talk to the people that agree with you in what's called an echo chamber, where everybody basically has the same opinions. And you don't get challenged on your opinion as a result, and you also are less capable of compromise as a result. So it's some interesting psychology and sociology, but it really does emphasize the importance of finding people you disagree with, not for the sake of arguing with them necessarily, although that can be fun too, but more for the sake of trying to understand their argument so you know whether or not your stance is good, and two, because if you can understand their arguments better, you have a better chance of convincing them of something in a civil debate. So I really like that question because, well, partly because I like arguing with people on the internet and arguing with people in general, but also because it is a good thing, good life skill to have, to make sure you're not just keeping yourself in your own little echo chamber. Make sure you're seeking out other opinions, other ideas. And then even if you don't ever change your mind, at least try to understand where they're coming from. Right? Because nobody has opinions that they think are objectively wrong, other than maybe taste in music. I can recognize that Kesha is objectively not very good, but God damn, I love Kesha. But that's pretty rare to encounter somebody.
It's so bad, it's great.
It's not even an ironic. So I was in grad school when it was cool to be a hipster and like things ironically. And maybe it started that way, but I really do think she's a really good songwriter and she is a good singer. But that's neither here nor there. All right. Crystals. Crystal healing. Do crystals truly have power people claim they do? No. There's no evidence that suggests that crystals actually have soothing energy or healing powers or anything like that. It is definitely a placebo effect, but don't talk down about the placebo effect though. Placebo effect is very powerful.
Oh, yeah.
So if somebody manages to, it wouldn't even be self-medicating, but if somebody manages to have amethyst crystals around and that helps them when they're feeling an anxiety attack come on, because they're convinced that the amethyst crystals have calming energy, who am I to say that they shouldn't have amethyst crystals because it's just a bunch of BS? Right? So the placebo effect can be immensely powerful, and it's really not that dangerous. It's not like they're doing any damage to themselves by believing in crystal healing. It only becomes a problem when people start trying to hawk their crystals or convince people to use crystal healing instead of chemotherapy. When somebody tries to say, no, I'm going to skip the chemotherapy because my chakras are more aligned when I have just put a crystal on my chest, that's when it starts crossing a line and maybe we need to have an intervention, or maybe that we're relying too much on the placebo effect at that point. But it is a fine line. You don't see me going around town yelling at all the hippies who are trying to sell crystals or anything like that, because for some people that's fine. These next few are all kind of tied to some things we've been talking about a little bit, so I thought they were worth going over. Can I explain the chemical reaction of an atomic bomb? Absolutely. It's actually a pretty straightforward one. Uranium-235, when it gets hit with a neutron, if that neutron gets lodged inside the nucleus of uranium-235, it becomes uranium-236. Which is hugely unstable. Uranium-235 is radioactive, but it has a half-life in the billions of years. Uranium-236 has a half-life in the microseconds. And it immediately splits into two smaller nuclei that add up to the same number of protons, plus 3 more neutrons. If those 3 more neutrons are now flying around, if they get embedded in another uranium-235 nucleus, you get a chain reaction happening, where every time that happens, it's got exponential growth, right? So most of the time, if you have a small amount of uranium-235 and this happens, then you make some uranium-236, it decays, fires some neutrons out, no big deal. But once you get above what's called critical mass, when you have enough uranium-235 in the same place at the same time, then there's more of these neutrons running to other uraniums than escape from your piece of metal. And when that happens, you get a runaway reaction, which is what we call a nuclear bomb. So that's where the term critical mass comes from. Below a certain mass, you won't get a bomb. Above a certain mass, it's almost a certainty you will get a bomb. It will blow up. Our nuclear power plants work by basically not getting to critical mass. They use the radioactivity to boil water, and when they boil water, it generates steam. They use that steam to spin turbines, and those turbines generate electricity. You wind up with big problems in nuclear reactors if you get too many of those fuel rods together because you get above critical mass. So the engineering winds up is a little bit more complicated than that, but that's basically all a nuclear bomb is. Enough uranium-235 in one place at the same time to cause a meltdown. There are other types of nuclear bombs. So hydrogen bombs or fusion bombs work using the same reaction that's in the sun, actually, where you take hydrogen and helium and fuse them together. You throw them together hard enough that you can get them to start a reaction where you wind up making other carbon isotopes, basically. And that actually releases even more energy, except that to get that process started, you have to use one of these. So basically, fusion bombs, they're called thermonuclear bombs because you use a nuclear bomb to set off a fusion reaction. So it's basically like a really, and then you use conventional explosives to start this process. So these hydrogen bombs are really, really complex because you have to get to a certain threshold to start that chain reaction. Once you do, they make a whole lot of energy released really fast.
What does it mean when people talk about enriching uranium?
So uranium is normally found as an ore, uranium oxide. And so taking that uranium ore and turning it into metallic uranium is part of the process. The other part is making sure that you get rid of the other isotopes. Other isotopes basically get in the way of this process. Because if you have uranium-238 in here and it absorbs a neutron, it doesn't go through the same reaction. You just get uranium-239, which is also relatively stable. So basically enriching uranium is basically getting to just uranium-235 or close enough to it that you can ignore that there are these other things mixed in that's slowing things down. And they basically do it with just a giant centrifuge. Uranium-238 is more dense than uranium-235. So if you spin it up to a couple thousand Earth gravities, a couple thousand G, you can actually get these isotopes to separate just based on their densities. And that's how that works. So overall, pretty easy reaction, pretty easy engineering, frankly. The Manhattan Project's biggest drawback was how do we enrich it and how do we get enough of it in the first place? And then the designing of the bomb was actually really straightforward. Jen?
So my son asked me, what's the difference between a nuclear bomb and an atomic bomb? Nothing, that's what I told him. Okay, so they're
Yeah,
the same thing.
same
Just
thing.
Same name or different.
Exactly.
Okay.
And that's partly because the word nuclear is scary to some people, and an atomic bomb gets that name because you're splitting the atom. It's going from uranium-236 to 2 smaller atoms. So they called it an atomic bomb first, and then they called it a nuclear bomb, and then nuclear had its own negative connotations, so they wound up changing certain things. Like an MRI stands for magnetic resonance imaging. It actually should be nuclear magnetic resonance imaging. But because everybody was scared of the word nuclear, they never put nuclear on the name. It should be an NMR. And we actually do NMR in organic chemistry because we can actually use it to measure specifically where specific protons and hydrogens and or carbons and other bonds are in a compound. Which in MRI is just doing that on a bigger scale using a computer to process the data. So it's, there's a lot of times we see multiple names for the same thing or the common name versus the technical name. And a lot of that just has to do with public opinion. And scientists need politicians to like them so that they can get funding. So we change the name of things sometimes. This was a good question because we talked about how hydrogen and helium form stars and how stars then go through fusion reactions to make everything heavier than hydrogen and helium. So somebody asked how do hydrogen and helium form? And again, that starts getting into a philosophy question because essentially it's basically asking, why does anything exist?
What came first, chicken and the egg?
Right. Well,
The egg.
why is
Egg
the
evolved
universe?
first.
Why is the universe?
Why is the universe is really what this question comes down to. And again, that's a philosophy question, although the scientists and the cosmologists might say because something is more stable than nothing. Mass is just another form of energy, right? And so if you don't have mass, you have all of that energy somewhere that doesn't have mass, that doesn't look like anything we could comprehend really. But it's more stable when it exists as mass than when it's just free energy. So one argument for that would be because it's more stable than not existing. But also cause and effect get a little bit muddled when you look at the Big Bang, because it turns out the Big Bang was a singularity, kind of like a black hole. And when you get to a singularity, cause and effect don't exist.
Yeah,
Time has no meaning.
it
There
just
is no
flattens up
time.
the time.
It does. Basically, there is no time.
Yeah.
Time does not exist on the at a singularity, where you have basically a black hole or the Big Bang. So if time doesn't exist, how can you have cause and effect? There's no before and after. So to say that it exists because it's more stable than not existing, well, that's sort of a cause and effect explanation, right?
Yeah.
And you can't really use cause and effect explanations when we're talking about things like the Big Bang. So, good question. And it also raises the idea of parallel realities, multiple universes, the multiverse. Those are mathematical ways to solve equations, such as what was before the Big Bang. First off, before the Big Bang doesn't make any sense because there was no time, right?
Yeah.
There can be no before the Big Bang because there's no time. How do you have before with no time? But at the same time, mathematically, it winds up causing some issues where you wind up needing to either assume that there's an infinite number of universes of which we are one, or we are one in a sequence of universes, many of which last longer than our universe, many of which last less than our universe. And we can't really discount the idea of the multiverse, but we also can't prove it. We don't have a way of testing it. We know that that idea makes the math work. But there are other assumptions you can make that make the math work as well. So we don't know which one's right. So it's basically not science at this point because it's not a testable hypothesis. If somebody came up with a way that would theoretically be able to communicate with another reality or another universe, Now all of a sudden we have something, well, if it works, then yeah, multiple universes. If it doesn't work, we're back to square one. We can't prove that they don't exist because you can't prove a negative. All that you could say is, and that applies to the afterlife as well. Somebody asked me about the afterlife. We can't prove that the afterlife doesn't exist, just that we haven't found any evidence for it yet. Right? You can't prove something doesn't exist. Otherwise, there wouldn't be people that still believed in Bigfoot, right? Not comparing religion to Sasquatch. I'm just saying the idea of
It's the same.
proving a negative. You can't prove a negative. So, anyway, let's get into more relevant stuff, such as why don't the electrons get pulled into the atom?
Protons.
Well, protons attract electrons, right?
The neutrons.
Neutrons?
Maybe, I don't know.
It actually,
Strong and weak forces.
strong and weak forces.
maybe.
We're just going through all the possible forces, right? It's actually the Heisenberg uncertainty principle, and I'll actually throw the actual equation up here.
We're just guessing over here.
The Heisenberg uncertainty principle, there it is. That's the constant. So your uncertainty in position times your uncertainty in momentum, which is P in physics, must be greater than or equal to h over 4 pi. Well, the nucleus is so small that if an electron fell into the nucleus, we'd be violating this because we would know both exactly where it was and how fast it was going, because it would be stuck to the nucleus because of the forces of the charge. The attractive force of having a positive charge next to a negative charge would basically make it stick. So essentially, electrons don't fall into the nucleus because then you'd violate Heisenberg uncertainty principle. So they're stuck in these orbitals, in these energy levels around the nucleus, because they can't get any closer without violating uncertainty principle. Which is weird. It seems like this is sort of just like a generic, okay, cool, it doesn't really mean, is this really provable? Turns out, yeah. This explains why orbitals exist. And there are also other ways they can measure this. And it winds up holding up, essentially, that you will never have electrons fall into a nucleus because of that uncertainty principle.
Did they get infinitely close?
They cannot get infinitely close because, again, then you would know their position and their energy with a great deal of certainty. But the bigger the nucleus gets, the closer those electrons are pulled. So remember from lab, there was that equation said that the energy of a system with a single electron is equal to the nuclear charge squared times the constant over the energy level squared. So as Z, and there was a negative one here too. As Z gets bigger, your energy is going to get more and more negative, right? More and more stable. You're going to pull it closer and closer to the nucleus. But you can never get it to go all the way to the nucleus. You can get them close enough that the electrons actually start moving at relativistic speeds, meaning at speeds a significant fraction of the speed of light.
So the closer it gets, the faster it goes, like in the solar system?
Exactly. It's the same rules of attraction, just instead of gravity, they're being attracted by opposite charges.
Would that explain why it's constantly moving as well? Because it's trying to get there, but it can't. So it's just orbiting.
Also ties back to this, right?
Yeah, right,
You
right.
can't know exactly where the electron is and know its energy at the same time. And we can know its energy based on what the temperature is. And so that means you're going to not be able to know exactly where the position is. So yes, it all does tie together that way. And one of the reasons why the Bohr model works so well and uses the idea of electrons orbiting a nucleus. They don't actually orbit it the way planets do. but they occupy a certain energy level, and they're somewhere in that shape. The same way that if you don't know anything about astronomy, but you know that Earth is 6 light minutes from the sun, we might not be able to look at it and say at any given point where it is in that orbit, but you could figure out it's about this far from the sun. And then it exists somewhere in that ring around the sun at any given point. But the math the reason they call them orbitals is because the math looks a lot like planets orbiting a moon, or sorry, a sun. So one more good question about, so this is a quick one. Just a reminder, when you do percentages, like the percent by mass on the ICA, the 100 is an exact number. So that's the definition of a percentage, right? Is you take this decimal and then multiply by 100. So that's exactly 100. So for percentages, your number of sig figs is going to be governed by the numbers that you plugged in, not by that 100. That 100 is exact. Just like if we have a density in grams per 1 cubic centimeter, we consider this to be a measured number and this to be an exact number. Because we basically are going to say, well, if we had exactly 1 cubic centimeter, its mass would be 11.34 grams plus or minus 1 here. We can kind of pick one of these to call exact, and the other one is a measured number. And then last but not least, more about neutrons. How do the neutrons in an atom's nucleus change within elements? Or why or how are there isotopes? Well, so that they don't change necessarily at any given point. So this is sort of an exception. For the most part, nuclear reactions are the exception rather than the rule. For the most part, when you have a specific nucleus, it's going to stay as that specific isotope, barring a nuclear reaction happening. So they don't usually change. It's just that you have a selection of different ways that are still considered stable. So if I pull up the stable isotopes, let's just use carbon. And I'll move it over there before I can see it. Isotopes of carbon. Wikipedia has its own page on isotopes of every individual element. There are a lot of different isotopes of carbon you can have. You've got carbon 8, carbon 9, carbon 10, carbon 11, carbon 12, carbon 13, carbon 14, carbon 15, and so on. They're not all equally stable, though. Most of these are unstable, and because of the ratio of neutrons to protons, is what's going to determine what's stable and what's not. Too many neutrons and it's not stable. Too many protons compared to neutrons and it's not stable. But there's sort of a sweet spot that's in between 1 neutron per proton and 1.6 neutrons per proton, depending on where you are on the periodic table. And if you stick to those ratios, you get isotopes that are relatively stable and likely to be found in nature. So carbon 12, carbon 13, and carbon 14, carbon 12 and 13 are the ones that are stable enough, we can basically say they don't decay. Carbon 14 is found in nature, but it does decay eventually, which is how carbon dating works. But these two isotopes that are stable because of the number of neutrons and protons. Now, neutrons don't affect the chemistry, they don't affect the charges, they don't affect what compounds you can make with those, but they do affect whether or not that compound is radioactive, whether or not that isotope is radioactive. Right, so the reason that different isotopes exist is because some ratios of neutrons to protons are more stable than others. Right? And in theory, we could have one isotope of every element that was the most stable, and we could, in theory, have a universe that was just those, and not much would change. But because our matter is basically made through chance and probability and statistics, we really get a range of isotopes occurring in nature. And that's sort of why we get those weighted averages on the periodic table for the masses. All right. So getting into new stuff. The biggest point that we want to get through today, where the heck, there it is. I need an actual mouse, or apparently I'm worthless at this. Is talking about how these electrons work and getting basically starting from the Bohr model, which is what we used in lab, and is what this equation comes from, or it explains why this equation is the way it is. The problem is that this only works if we have a single electron. The second you have more than one electron, this model goes out the window. Because we have a nucleus, which is positive, we have an electron that's negative, and they're attracted, right? And the different energy levels you can have are like those harmonics on the guitar. It has to be at one of those integer values for it to work. But the second you add another electron, you've got the electron being attracted to the nucleus, but you've also got the electron pushing away the other electron. Because the electrons are all negative, right? And negatives push away other negatives. So, I don't know, is Among Us still a thing? Does anybody still play Among Us anymore? So what if an atom has more than one electron? Bohr, emergency meeting. Basically, Bohr shuts down. Bohr doesn't work. Bohr's model does not work the second you have more than one electron. But our understanding of the idea of energy levels does. We just can't calculate those energy levels by hand. Right? So that's when we get into these different types of orbitals. They're going to have different shapes. And going along with those, they're going to have different energies. The energy of an orbital is based on how far it is from the nucleus and how curved the shape is. Think about those guitar strings. Those guitar strings went up in pitch. The more curvature we had, they went up in frequency, right? They went up in energy by adding more curvature to the shape of this function. Orbitals behave the same way. As you add more curvature to the shape of these functions, they get higher in energy. Right, so that tells us that we're going to be using math and sort of this idea of different energy levels to explain why the periodic table is shaped the way it is. Right, so every time you go up in energy level, you add a new type of orbital. So when you're at the first energy level, you only have one type of orbital. And that's why the first row on the periodic table only has 2 elements in it. You only have one type of orbital, and it can only hold 2 electrons. Once you add 2 electrons to your first energy level, it's full. We have no more room in the end. Can't put any more electrons in there. So what do? Well, we go to the next energy level. And again, this isn't working. So once we fill up the 1s orbital, we go to the second energy level. We still have another s orbital. There's another sphere shape that we can use to fill up electrons that the electrons can occupy. But there's also this additional orbital type. There are those ones that look kind of like a figure 8 that we talked a little bit about the other day. And what that corresponds to is this right-hand section of the periodic table. So this is labeled as the P block, you may have noticed while you were studying for your quiz, right? The P block is because it's named that because that's the type of orbital that corresponds to adding that many electrons. So when you add 2 electrons, you're filling up the first energy level. When you add 3 electrons or 4 electrons, you're in the second energy level, but you're still in an s orbital. So you're still in the s block. If you follow the periodic table, you follow the atomic numbers, number 5 jumps over to the p block. So our next type of orbital has 3 different places it can put electrons. They can hold 2 electrons each, and we call it a p orbital. All right, so the p block corresponds to adding electrons into a p orbital. And once that's filled up, we have to go to the next energy level. Now we're back in 3rd energy level. And we're putting electrons into an s orbital again. It's just the 3s, not the 1s or the 2s.
Well, by that chart, isn't helium technically in the p block?
It is, but because it has so many similarities in terms of reactivity with the other noble gases, we put it here because this column corresponds to having a full p orbital, or just being really, really stable. So it doesn't have a p orbital. So electronically, in some periodic tables, especially older ones, will actually have it listed in 2 places.
Okay.
According to the electrons, it should be over here, but according to the properties we can actually measure, it makes more sense to put it with neon and argon.
And is it everything? Oh, but then the F block is just its own. It's not in the D. Okay.
And then the F block actually fits in between the S block and the D block. Right, so on my periodic tables, I try to indicate that by using this sort of extra bolded line. It says, really, these should be pulled apart. Problem is that doesn't print well on a piece of paper. So basically, because of the limitations of the way we bind books and print things, it made more sense to pull out the F block as though it was something totally separate. But it's not really. All right, so here's another way of representing these. Sometimes you see these energy levels, these orbitals represented as boxes instead of lines. It's the same basic principle. Each one of these boxes can hold 2 electrons. And your lowest energy orbital is going to be the 1s orbital. You're always going to fill up the 1s orbital first. Once that's filled, if you still have more electrons, you got to put them somewhere. So you put them in the 2s. Once that's filled, we have to put them somewhere, so they go into the 2p. All right, so effectively, if we can actually predict what the electronic configuration is by basically just counting on the periodic table. All right, so there are other methods of doing what are called electron configurations. But to me, since periodic table is your safety blanket, and I'm never going to take it away again now that you're through today's quiz, knowing how to use the periodic table is more valuable than learning one of these other strategies that you have to remember how to draw it properly on a test. So I'm going to teach you predominantly this way. All right, so the way that we write these is we want to indicate how the electrons are arranged. We just use a notation where we put these exponents, or the number of electrons in each orbital we're talking about. So you start by saying what energy level it's in. Then you say what type of orbital it is. And then you say how many electrons it has. And verbally, we would just say 1s2. So the electron configuration for boron, which is number 5, is it means we have 5 electrons, right? So we're going to start the lowest energy orbitals and just fill it in until we run out of all 5 electrons. So the lowest energy is always 1s, and it can hold 2 electrons. Go to the second row of the periodic table, and we're in the s block. And it can hold 2 electrons before we get to the end of the s block. We still need 1 more electron. So we can say, okay, well now we're over in the p block. It's still in the second row of the periodic table. 2p, and there's only 1 electron left. 2p1. So this is what we consider is what we call an electron configuration And it's basically a shorthand for actually drawing out those energies. Instead of writing out the energies the way I first presented this, and saying 1s, 2s, 2p, instead of drawing this out every time you want to talk about how the electrons are arranged, that's a convenient shorthand. Because the shapes here are never going to change. They always go in the same order, and they're always going to hold the same number of electrons. So if we can learn those rules like p orbitals can hold up to 6 electrons, then using this is actually just a lot faster, takes up less space, more convenient way to write how the electrons are arranged. So let's do some practice. With that in mind, and with your periodic table if you have it, which everybody does because you studied for the quiz from it, right? Almost like I planned this out. Everybody has a periodic table now, so everybody can write electron configurations too. If we want to know the electron configuration for oxygen, we count along on the periodic table until we get to the right number of electrons. Oxygen, when it's neutral, has 8 electrons, right? Mm-hmm. So we need to add enough electrons that we get up to 8 total. So for oxygen, that's going to look like it's always going to start with 1s2. The only time it's not going to start with 1s2 is if you're talking about a hydrogen atom. Then it's just 1s1. So oxygen, 1s2, and then we finish the first row of the periodic table. Now we're at second row of the periodic table, so 2. We're in the s block. So that tells us we're adding electrons to an s orbital, and it can hold 2 electrons. So 1s2, 2s2. Now we're in the p block, still in the second row. 2p.
4. Oh, I mean 2.
No,
4.
Yeah.
You were right for the first time. It can hold up to 6. And if we needed to add more electrons, conveniently, the p block ends, and we're back to starting on the third row now. Right, so the reason that the periodic table is shaped the way it is, the way Mendeleev structured it, is because that corresponds to the orbitals and how many electrons you can put in each orbital, which also corresponds to measurable physical properties. Do you have a question, Dylan?
Yeah, I think we're about to answer it.
Okay.
I'll wait till.
One thing I will also say, we actually have rules for how we do fill these orbitals up. We always will wind up adding electrons with they have what's called spin, which does not mean the electrons are physically spinning. It basically comes from the fact that electrons have angular momentum, and the math for that looks a lot like a ball spinning. And if you have a ball that is spinning, it can spin one of 2 ways, right? If you spin a basketball on your finger, it can be spinning clockwise or counterclockwise and still have the same energy, right? So this is why we can put 2 electrons into each of these boxes, is because one of them will be spinning one direction and the other one will have the opposite spin. I know I just said spinning, but they're not physically spinning, that's just what the math looks like. So, and we always will fill these up with them all having the same spin before we double anything up. And it's a little bit like, the analogy that I use to remember that is it's like seats on a bus where nobody knows each other. If you're going to put 10 people on a bus with 10 seats, every seat will have 1 person in it before anybody wants to double up, right? So if we're looking at oxygen that has 4 electrons in this p orbital, we fill it up like this. And now we need 1 more, so we pair it up. Turns out that having them filling up the orbitals halfway before you fill them up completely actually has important implications. Turns out that's actually where magnetism comes from in metals. metals that have a bunch of unpaired electrons that all have the same spin generate a magnetic field. Because the spin on these electrons, even though they're not physically spinning, is what generates that magnetic field. So you will always fill them up pointing the same way first, because that's kind of more stable than having them all random. When they're pointing the same way, then they're generating that magnetic field together, and that makes them a little bit more stable. Right, so when we fill these up, sometimes, at least once, I will ask you to do a diagram like this, where I say, here's the diagram, I will give you the orbitals, and say, draw the molecular orbital diagram for carbon, or for chlorine. And you will just add enough electrons till you get there, but you want to fill it up the right way.
I was actually just going to ask, if you're filling up, let's say that one specifically, would I do the half on the 1s, the 2s, and then all the 2p before I go back down to the bottom? Or do I just go 1s, 1s, 2s, 2s? And then...
So because these are different energies, you will fill them up before, before you wind up putting anything up here.
Okay.
Because even though we're forcing them to be paired up, this is the most stable orbital. This is the most stable place to put electrons. So in our car's seat analogy, this is like putting two people into a sports car. Okay, yeah, you could take two sports cars, but it's really more stable to just make them pair up even if they don't know each other, right? And I guess it depends on who we're talking about here, but let's make a blanket no serial killer assumption about our random people we're talking about.
Like that's in the model for oxygen up in already?
Yeah, and this is the shorthand for it. So when I say draw or write the electron configuration, I mean this. So if I say fill in the molecular orbital diagram or the atomic orbital diagram, I'm talking about this. Right, but they really correspond one-to-one to each other. It's two ways of looking at the same thing based on what's convenient. How about selenium? Actually, selenium's a tricky one. Let's wait.
1s2, I got it.
Let's do magnesium first. So magnesium is going to start a lot like oxygen, right? 1s2, 2s2, 2p6, 2p6, and now we've filled up the second row of the periodic table, and we're going to the third row of the periodic table, but back to an s orbital.
So that's how you do it.
Yeah. Neon looks the same as magnesium except without these. And neon only has 10 electrons, which means when you get to the end and you fill up that p orbital, you're done. So neon would be 1s2, 2s2, 2p6. Total of 10 electrons. And that corresponds to filling the second row of the periodic table, the second energy level. So remember when I told you that every time we go up an energy level, we add a new type of orbital? We went from 1 to 2 and we added a p orbital. When we go to 2 to 3, you add a d orbital. The problem is, and I'm going to erase this and expand it so I can show with a little bit more detail here. So if we had 1s down here, 2s, 2p, 3s, then 3p, then something funny happens. The 3d orbital is higher in energy than the 3p, and it can hold a total of 10 electrons, so it's 5 lines. The thing is that 3d orbital is actually higher in energy than the 4s. It's essentially, to go back to our guitar analogy, we've made the note so high on the third string that it's actually lower in pitch to go to the fourth string. Right, so because these s orbitals are just spherical shaped, they're lower in energy than any other orbital type at that energy level. And so when you're filling these out, the first d orbital that you see is in the fourth row of the periodic table, but it really belongs to the third energy level according to the map. So our periodic table is designed based on what we see experimentally in the real world. But if we were trying to do something like selenium, we actually wind up filling up the 4s orbital before the 3d orbital. All right, which makes things look a little bit weird.
Why is it 3D if it's the first row of D that we even have?
So
Same reason it's 2p when it's the first p that we
the
have.
first P that we had was in the second energy level. The first D we have is in the third energy level, and the first F that we have is in the fourth energy level. So we're going to actually keep adding new types of orbitals as we get to higher energy levels. And that makes this part a little bit tricky. And it makes the electron configurations a little bit tricky. So for selenium, selenium's down here. Fourth row of the periodic table. 34 electrons total.
1s2, 2s2, 2p6.
So start 3-4. Right, so that part doesn't change. It's just that weirdness with 4s being lower than 3d. And in a similar way, 5s is lower than 4d. Right, so the d block is always offset by one energy level from where it should be. It shows up in the fourth row, but it's really the third energy level.
Question.
Okay.
Why can't we just say that selenium is 4p4? Because if it's the only one that can be 4p4 because of the periodic table and whatnot, why do we have to write up this whole equation if selenium can only be 4.4 or 4p4?
Because if you change the number of electrons something has, something else could have that electron configuration too.
Oh, so that's like the
Looking
oxygen
at
2
that
negative.
one.
Okay.
Oxygen with a 2 negative
Okay.
has 2 extra electrons, which means all of a sudden its electron configuration looks just like neon. Because oxygen's right here, if you give it 2 extra electrons, it's got 10, which means it's going to look like neon. So this part gets really repetitive. And I'm going to tell you the rule for using an abbreviation for this. In this class, if I ask you to write the electron configuration for something with 18 or fewer electrons, I want you to write it all the way out. You'll break now. Seems less awkward and get some practice.
Seconded.
Okay.
So with the F block, kind of going ahead a little bit, would that have a higher energy level than the 4D? 4F would have the higher energy, so you'd have to fill up the 4D first?
Yes, so anytime you get to the 6th energy level and you start filling it in, so let's do lead as an example. Lead's down here at 82. We just used that for one of our ICA problems, so we all know where it is. If we wanted to write the electron configuration for lead, I'm going to erase this too, there at board space. And I'm going to write it completely, the complete electron configuration for the sake of practice for you. Starts at the beginning and it gets repetitive. Hopefully it gets so repetitive that you're saying this in your sleep at night. 1s2, 2s2, 2p6. Right, so it's the same every time. We're at the end of the second row. 3s2, 3p6. End of the third row. 4s2, 3d10, 4p6. Now we're at the end of the fourth row. So we're at krypton now. Fifth row doesn't have anything different than the fourth row. So 5s2, 4d10, 5p6. Gets us to the end of the fifth row.
That answers my question.
Okay, and that gets, so now we're at xenon. And from there, 6s2,
F.
follow the numbers on the periodic table. The numbers on the periodic table go from 56 to 57 down here. So now we're in an F orbital. And just like we were offset by one spot with the D block, we're offset by two spots with the F block. So it's 4F, 14.
Tricky.
All right, so, and now we're back to the D block. That gets us to right here. The ytterbium. And now we're back in the D block, so we're only offset by one spot.
So 5D10,
5d10.
P, 5P2,
And now we're in the P block. And now we're at the end game, right?
6P.
Lead's right here. There's only 2 electrons left. We're in the 6th row, so P block still is everything's good. It only takes 2 electrons. That's the complete electron configuration. The abbreviated version would look like starting at xenon. So now we're at 6s2, 4f14, 5d10, 6p2. All right, so I know that that's pretty abstract and kind of has a little bit of an element of just take my word for it with the energies. We can calculate these energies. They work out. This follows all sorts of measurable quantities. It's just weird. In the way that I always remember that these are offset from where they're supposed to be is that rule. Every time we went up an energy level, we added a new type of orbital. So we got our first d orbital has to be 3 because that was on the 3rd energy level that we added a d orbital. Our first f orbital, even though it shows up all the way down here, has to belong to n equals 4. Because mathematically, that's the first place that an f orbital can show up. And we can actually predict orbitals that we can't see. We can predict the existence of g orbitals. A g orbital is what happens when you go from 4 to 5. So 2 to 3 added a d, 3 to 4 added an f, 4 to 5 adds a g. There should be a 5g orbital. It's just so high energy we never actually observe it. We haven't yet. But mathematically, the functions exist, and they say they belong to the 5th energy level. And so it's always just a matter of, okay, my first d orbital is actually n equals 3. My first f orbital is actually n equals 4. Right, that's the trickiest thing about these.
And with regards to noble gases, those are the only ones that you can use for shorthand?
You see them used sometimes, anytime you get to a full orbital, sometimes you'll see a shorthand. I don't prefer that way of doing it, but for instance, like thallium, some periodic tables have the electron configurations written on them. Sometimes you'll see, okay, well, mercury corresponds with finishing up the 5D. So you would say, okay, mercury, and then continue on from there. The ones that are most common, though, are the noble gases. That's the ones that I want you to worry about using as an abbreviation. Be aware that other versions exist, and anytime you see something in brackets like this, that's what it's saying. All right. What happens with ions?
Just count the electrons.
The electrons change?
Number of electrons change, right? So exactly where you stop counting on the periodic table can change. If you've got a negative charge, you've got extra electrons, right? But our rules for filling up our orbitals don't change. So if you want to know what the electron configuration for sulfur with a -2 charge is, sulfur is right here, the third energy level. I would generally start by writing the electron configuration for the neutral atom and either add electrons or subtract electrons once you get there. So sulfide with a -2 charge, start by just doing regular neutral sulfur. 1s2, 2s2, 2p6, 3s2, 3p4. Gets us the sulfur, total of 16 electrons. If we're going to add 2 more electrons to it, though, we don't actually have 4 electrons in the p orbital. We have 6.
But it was the opposite. It has a positive charge, it's not less electrons.
Correct. So sulfide has a -2 charge.
Oh, I'm sorry.
And if it does have a positive charge, you do the opposite. You're going to be taking electrons away.
Sorry, I wrote the wrong thing.
So calcium with a +2 charge, calcium starts out looking like it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. If it has a +2 charge, it's missing 2 electrons. So which electrons do we take away? Yeah, the ones that are highest in energy.
Could we just use shorthand for that and say it's the same as argon?
That's why I said specifically more than 18,
Okay.
because argon is 18.
Right.
So but yes, you will see people sometimes write it as, okay, my electron configuration even for sulfide, or not the brackets, is argon. And just leave it like that. I don't want you to do it that way. So I'm specifically telling you it has to go more than 18 electrons before you're allowed to use the abbreviation. Because if it's argon or less, I want you to write it out. So you'll get very, very good at writing out these 6 orbitals in order, 5 orbitals in order. Right? All right. What do we do with zinc? Let's do zinc neutral and then do zinc with a +2 charge. So I'll give you guys a few minutes head start. Zinc is at the end. It's right here. It's number 30.
Can we do the argon trick?
Sure. More than 18 electrons. That's valid.
Is that it?
So for neutral zinc, it should look like this. Or if you're using the abbreviation, argon, and then 4s2, 3d10. Remember that d orbital is offset by 1 spot. So this is zinc when it's neutral. Either of these 2 options is fine. What about zinc with a +2 charge? Our normal rules would say we would do 3d8. And here's where I'm going to amend them. Full orbitals are more stable than normal. Basically, once you fill up an orbital, you're never going to break that filled orbital up again. So if our choices are, and the bigger the orbital, the more that matters. A full d orbital is exceptionally stable. A full p orbital is really stable. A full s orbital is pretty stable.
So we're getting rid of the s orbital.
So we're getting rid of the s orbital. Instead of dealing with a full s orbital and a partial fill of the d orbital, we're just going to get rid of the s orbital instead. And then we're still only dealing in full orbitals too, right? We don't have anything that's partially filled. So zinc with a +2 charge is going to be argon 3d10.
So if you write 4s2 3d8, are you wrong?
You're half right. You're wrong, but in terms of partial credit. So I realized that was not a good way to answer that question. No, that is wrong to do that. And we'll see that with pretty much all of the transition metals. And this is where it gets past where we got in Chem 100. Chem 100, I basically just said d orbitals are full or empty, and I'm not going to ask you about anything else because the d orbitals get weird. D orbitals are still, they're most stable when they're all the way filled, and that gives them a big boost in stability. So if we're taking away electrons, it's usually going to be from the s orbital if we're talking about a transition metal, which is the whole D block is called the transition metals.
To take that one step further for the f block, what would you take away from them?
So if your choice is break up an F block or break up a D block, you're better off breaking up a D block.
Would it go to break up the P block though, that is before the F?
I don't think those things don't wind up being stable enough that we see those very often.
Okay.
So like something with a barium with a +3 charge basically doesn't exist because you would have to take away these first two electrons and then break up a really, really stable orbital to do that. So basically, and that's why we wind up with a lot of these things wind up having the same electron configurations, is because those electron configurations are more stable than others. So calcium and sulfide both had an electron configuration that looked just like argon, right? Because argon corresponds to having a full p orbital and no partially filled orbitals. So things over on this side of the periodic table are going to usually try to gain electrons to become more stable. Things over here are going to try to give away electrons to become more stable. And that's actually the difference between a metal and a non-metal, is whether or not it gets more stable by giving away electrons or accepting electrons. Things that pull electrons towards themselves in this corner are called non-metals. Metals always get more stable by giving away electrons. To get to having only filled orbitals. It turns out exactly halfway filled orbitals are actually stable too, especially when you get to the d orbital.
So if it was just zinc with a +1 charge, would you just have 4s1 3d10? Or is
Yes,
that not-
although we don't, that's not something we ever will observe in nature, because we went from having full orbital and a full orbital to having a half-filled orbital. This is super unstable. If we could take away just a single electron from zinc, it immediately will find another electron somewhere and go back to being metal zinc, or it'll give away its other electron.
But that's not how we would write it, right? Because the 4s has to go before the 3d.
So that depends on which book you look at.
For your book and grading.
For my book and grading, they're the equivalent.
Okay.
You can put 3d10 then 4s. So if we go back to things, that physically hurts me to write 4s1 there for zinc. So you can write 4s2 3d10 is the way that we filled it up. A lot of books will keep all of the 3s together and then put the 4. And so that kind of corresponds with how you would take electrons away from something. I'm not picky about either of those. Writing it 4s2 3d10 or writing it 3d10 4s2. You see those about equally depending on which textbook you're looking at. Right, so I'm not going to be picky about that.
You're gonna do bromine?
This is just because electrons are the only thing that matter in chemistry, unless you talk about nuclear chemistry. This is never a wrong answer in chemistry. When something happens, it's always electrons. Might not be specific enough for full credit, but you're not wrong.
So you get partial credit.
Partial credit and make sure that.
Yeah. So, and then we'll do bromine with the -1 charge, and then we'll be done for the day. So bromine is 1 away from the end of the 4th row. So when it was neutral, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3p10, 4p5. When it's got a -1 charge, 4p6. And that makes it more stable because now we have only completely filled orbitals.
So bromine with a -1 charge is more stable.
It is, which is why bromine and chlorine in particular, when they're neutral, they get used as disinfectants. That, why we use chlorine in pools is basically because chlorine as Cl2 is so reactive because it really wants to gain 1 electron. And in doing so, it doesn't matter if it denatures proteins that are making up the cell membranes of bacteria floating around, or of your lungs. So it's not good to breathe chlorine or bromine for the same reason that we're talking about here. To get it to be more stable, we get 4s2, 3b10, 4p6.
Because it's a full bracket, can we use your trick and do the bracket crypto?
So I would prefer that you show me that.
Okay.
Generally speaking, I want you to go 1 level up. I don't want you to just use the brackets on anything. Right? And pertaining to the quiz, I know I said we're done, but just watch out on the quiz. I have you do 1 complete electron configuration for a big element. Do the complete, meaning all of it. Don't use the abbreviation. I want you to practice that. Okay? All right. Have a good weekend, everyone. I'm here until 4:30 if you guys have more questions on ICAs or labs or anything. I do not have a stapler.
I got my name on both.
Okay, perfect. And I don't have any of those collected yet, so you're the first one. So perfect.
I had a question. So for the F blocks, so since the D block starts at 3 while everything else is 4, what does the F block start at? Because I know everything, there'll be 6 S2, 5 D10. Will it be 4?
Wasn't able to finish it.
Yeah,
Should it be 1 more lower than D block? Okay.
exactly.
I just thought I'd be completely.
And then also, for sig figs, say you're using like a constant, like Planck's constant, since it's defined as 6 point whatever, it's 626 times 10 to the whatever, is that infinity or infinite amount of?
No.
It's 4?
It's 4.
Okay.
Because if you added more, it's like pi.
Okay.
You can go look up more digits. If you
Yeah.
need more significance, you have to go look it up.
Okay.
But it's not exact. If we write it as, if we say H, that's considered exact because that's a fundamental constant. See it, Dylan? That's a fundamental constant of the universe, just like pi. But the second you try to plug it into your calculator, you've got to carry as many digits as possible.
Sure. Okay.
Usually 4 will be enough.
Gotcha. Okay. That's for my 2 questions of the day.
Cool.
I'll see you next week.
Sounds good. See you then.
Sean, I just got a quick question for helium.
Mm-hmm.
How would you write that? It's the